This is Mount Kilauea, Hawaii's most active volcano. 3 years ago, scientists were taken by surprise when lava began spewing out from cracks in the lower slopes of Kilauea, 50 kilometres from the volcano's summit.
The rate at which it produced new lava was almost unprecedented in historic times. So it wasn't so much the sheer size of it, it covered a very small part of the state. It was the speed with which it did it.
In total, 1 cubic kilometre of lava flowed out over 3 months. Rivers of runny lava ran down to the ocean, destroying hundreds of homes. Volcanologists like Bruce Houchen and Matthew Patrick have been studying Kilauea for decades.
This is the best monitored volcano in the world. So Matthew probably wouldn't say that to you because it would be a boast, but it's not. It's the most intensely monitored volcano, and then it had a very intense eruption.
This makes Kilauea the perfect volcanic lab for studying how eruptions happen. Since the 2018 eruption, the team have been piecing together the events that triggered it, so that next time a volcano of this type erupts, we can be better prepared. Kilauea is a basaltic volcano, which means it has very fluid magma below the surface and tends to leak runny lava rather than erupting explosively. At the summit, there's a crater known as Halemaumau. Lava has been bubbling to the surface of Halemaumau since 2008, forming this lava lake. Nearby is another crater called Pu'u'o. Lava has been slowly flowing out of Pu'u'o and down to the ocean, almost continuously since 1983. To the east of Pu'u'o is an area called the Lower East Rift Zone. The last eruption in this zone was in 1961. After that, it became a popular place to live, partly because the land here is cheap compared with the rest of the island. But this is where the lava flowed out in 2018, taking residents and researchers by surprise.
We had seen the pressure building at Pu'u'o and the summit, and we were expecting a relatively small change at the Pu'u'o eruption site. But in 2018, for reasons that I think we still don't fully understand, that pressurization triggered a bigger change, a deeper change, that presumably cleared a blockage that had been restricting magma moving east of Pu'u'o. On April 30th, we started to see earthquakes migrate east, down rift. So those earthquakes migrating down rift were a clear sign that magma was intruding through the volcano farther down the rift zone. It was a clear indication that something new and something potentially very hazardous was happening.
On the 3rd of May, the first cracks or fissures appeared in the Lower East Rift Zone. Bruce rushed over there.
The notion that something driven by processes under the summit of the volcano is going to create something 50 kilometers away is hard to encompass. But once the fissures first formed, I was confident that they were going to propagate outwards, that you would open up one, then another, then another. And what I really wanted to do was to be around for as many of the fissures opening as possible.
Bruce used high-speed cameras to film the gas and particles that were spat out from the fissures first, before the lava flows got going. Back in the lab, by slowing the footage down,
we get the size of the particles, the shape of the particles. We also can measure exactly how much is being erupted per unit time. So the estimates of intensity come from those videos as well. We just measure the total amount of material that's in the air at any second.
Another team analysed the chemistry of the lava itself and realised that in those first weeks it was cooler, stickier old magma coming out. Once that was flushed through, they predicted that hotter, more fluid magma would arrive from the summit magma chamber.
And I remember being on one of the first overflights after that kind of change happened in the eruption. And I had never seen so much lava on the surface. And once we started to see the arrival of this hot fluid magma, the hazard of the eruption totally changed. And unfortunately, it became much more destructive.
The lava covered farmland, roads, and around 700 houses, reaching the ocean in early June. Meanwhile, at the volcano's summit, another historic event was unfolding. The crater was collapsing as magma from the reservoir underneath it drained away to the eruption site.
There have only been a handful of caldera collapses that have been monitored with modern geophysical instrumentation. And what we saw is that the caldera collapse was not just one big event. Basically, every day or so, we saw the crater floor drop several meters.
Each time the crater floor dropped, it caused an earthquake with a magnitude of about 5.3. It also briefly pressurized the magma chamber, and that sent out a pressure pulse down towards the lower East Rift Zone, which caused a surge in the lava that was flowing out there.
It was really remarkable to see the changes happening at the summit, then being transmitted basically within minutes to produce these surges in lava eruption rates down on the lower flank that had direct implications for hazard.
I think the biggest thing that we've learned is just how connected all the parts of the system are. So a lot of people now are revising their models for how you get molten rock to move, not simply vertically under the volcano, but how you get it to move 50 kilometers relatively rapidly and reappear somewhere else. Because that's the part that we have least understanding of, because it's the part we can't see. At the moment, volcanology is all about basically simple pattern recognition. It's not about understanding the processes, the mathematics, or the physics of what's going on. And that's what we're trying to transform into.